Hi, and welcome to the poster for proposal of a magnetic racetrack-based temporal memory for race logic. I am Samiran Ganguly, and these are the rest of my colleagues and the co-authors on this work. And me, Samiran Ganguly, Mohammad Saqib, Hamid Wakili, Mircha Arstan, and Avik Ghosh. We are all from University of Virginia. Advait, Madhavan, Matthew Daniels, and Mark Stiles, they are from NIST. Advait is also additionally affiliated with University of Maryland. And please welcome to our talk. Let me get started. So what is a magnetic racetrack? Magnetic racetrack is composed of this structure on the left as I'm showing. It's on the top is a ferro or a ferrimagnet. It's like say an alloy of cobalt and iron. Coffee bees is popularly called. It's a very popular material in magnetic industry, in MTJ world, in spintronics world. And on bottom, if you can put a heavy metal like say a platinum or a tantalum, this combination have been known to have shown that there's this phenomena called spin orbit torque. So what I'm showing using these blue arrows of that some spin can be injected into the ferromagnet from the heavy metal layer. So this has been quite well known and people have been working on spin orbit torque. But what is interesting is that if you make this structure, this film of these two layers, long rather than wide, so like a very long strip, so that's like a racetrack. Why is a racetrack? It's called a racetrack because if you drive this current underneath, the spin orbit torque can drive a magnetic excitation along this track. So now what do I mean by magnetic excitation? So let's consider this whole ferromagnet as pointing downwards. So we can show that you can excite a small region of this magnet, as I'm showing in this figure, to be up spins. So if you do that, that's like an excited state of the magnet in that small region, and you can confine it and you can move it around. So that's why it's topological. And I'm showing you some examples on the right of skyrmions. They are a type of a topological excitation. There are others like bubbles and domain walls. So domain walls have been popular. They have featured in DRC as well previously in other devices. A lot of proposals have been made using domain walls. Consider skyrmions as a small size domain wall which does not extend from end to the end of the magnet. But the main principle is that the central point is that with this drive current underneath the heavy metal, you can make this excitation move left and right controllably. Now, people have proposed high-density binary memory bits using racetracks, especially Stuart Parkin's group came up with the racetrack memory initially using domain walls. Our proposal, we are storing a special kind of an information, what we call temporal or time-like information on the track. And what do I mean by that? We'll go into details in this poster, and you will see in details. But before we do that, why do we care about storing what is called this temporal information? We'll take a quick detour of what is race logic, one of the target applications for this proposal. So this is a race logic in brief. Essentially what race logic does is that it encodes any kind of information that you are dealing with as a binary wave arrival time. What I mean is that consider these two waves A and B, two binary lines A and B. And you can see that the B went from 0 to 1 before A went from 0 to 1. So this 0 to 1 transition time is the temporal information. So this is the arrival time. When does the bit arrive onto a certain line or to a certain gate? So if you do a OR gate on it, as we show in the bottom, so of course B dictates this because B arrives first. So if B is 1 and A is 0, you still get a 1. So therefore the OR gate acts as OR gate will show B, or in some sense, if you think about it, it shows the which bit has arrived first. So it's the min function, the min of the arrival times of these two. And similarly, AND gate will show A because both have to be 1 at certain point of time. That's when it will turn on. So you can see that with this kind of an encoding, AND gate acts as a max function, which is what is the maximum of A and B. So this is useful in a lot of dynamic programming examples of graph theory problems. For example, if you want to find two different path lengths, say between node A and B, separate from this A and B bits, say node A and B, and you have different path lengths. So you can use this information, for example, to get what is the minimum path length through which this problem occurs in this graph. So these kind of problems can be solved with race logic pretty quickly, because you're just encoding the information in a special way. So it has one of the applications I'm showing you is this DNS sequence alignment. You can please go and look at this reference. It goes in details about race logic and how you can actually do dynamic programming algorithms, especially on a DNS sequence alignment. So let's go on to the actual proposal that we made. So this is the proposed memory cell schematic. Now it looks a little bit busy, but the central principle, as I'll describe, is actually quite simple. So we consider two racetracks. So one we denote as the main racetrack, where all the action happens, in the sense that that's what is used to read, write, and all those information storage is done. But we also have a recovery racetrack, and I'll come to a minute why recovery racetrack is necessary. So there are four possible operations. A write operation, in which you basically you have an incoming signal, this T1, and it turns out this transistor T1. So on the right, I'm also showing the table, the control pattern that you need to apply. So you essentially, what you have is the bit line is on, and you have this transistor T1 turn on when the signal arrives, and this, you can see that it will drive the main racetrack's heavy metal current, and that will drive the skyrmion. Okay, so this is easy to see. And then when you apply the read operation, what you do is that you can, again, you have the bit line turned on essentially, and what you do is now you also have the read enable turned on, this blue thing turned on. So what happens is that now the skyrmion is driven wherever it was after the write operation to the end of this the racetrack, where you have this MTJ sitting. So now what happens is that when the skyrmion reaches the MTJ underneath the racetrack, the MTJ's resistance changes, because that's how MTJ works. It sees a different resistance depending upon the orientation of magnet underneath, or orientation of the racetrack underneath. So it reads it, and there's a read enable, so you can actually read it, and you see a V out, voltage out, and this basically turns off this transistor. So that you stop every operation, and whenever that blip happens is when you have recovered the time. So you can see that if you have a clock cycle, if you assume a large clock cycle and your information storage is within that clock cycle, you can see that you can drive this skyrmion for a certain amount of time, and when you make it go to the other end, you recover basically the complement of the time, and then you can make it work in a certain way, in a transistor in a certain way. So what I'm showing now is the importance of why you need a recovery racetrack. So what happens is that once the skyrmion has moved to the the MTJ reader on the end, you have forgotten. There's no way you can store that information where the skyrmion was. So what we do is that in parallel to this driving of skyrmion on the main racetrack, we also drive a skyrmion on a coupled recovery racetrack. So the skyrmion on the recovery racetrack is always at the beginning, as it was in the right condition on the main racetrack. So we drive both of them the equal amount during the read operation. Therefore, that complement thing, as I was saying, so if you drove it to say W length, and then the racetrack is L length, so L minus W is what is going to be read, the time, equivalent time. So you're going to drive this recovery skyrmion also for the same length, L minus W. So that is how you basically, you have now encoded that W information, whatever it was, in the recovery racetrack. And now you can drive it backwards. During the recovery phase, you can just drive these current backwards. So you see that the bit line and the select line, the polarities have reversed in the recovery. So therefore the current is flowing in the negative direction. And you do that again, and then again, once the recovery skyrmion reaches this the initial point, it triggers this voltage, and this voltage triggering will shut down the circuitry. You can actually follow the signals, and you can see that this actually happens, and I'll show you in a simulation that it does work. And then the erase simply is that you do not do anything with the recovery racetrack, you just drive the main skyrmion racetrack back. So using this recovery racetrack, you can actually repeatedly again and again read the same information. All you have to do every time you do a read, you just do a recovery racetrack, a recovery operation, and you get your signal back. I should mention that now this temporal information is volatile. That's why you require a recovery. But the skyrmions themselves are non-volatile. They have a certain amount of lifetime. They can last from anywhere from nanoseconds, milliseconds to even years. People have found magnetic bubbles to stay for years. So you can have a different kind of a time scale. So that information that you wrote, that W, that information that you wrote in the right information, that can just be itself on by itself. It can stay for a long time, so it can act as a non-volatile memory cell. It's only that when you do a read operation, you have to restore the information back. So that's why it's volatile in the bit and the information that you wrote only if you read the information. Otherwise it's a non-volatile memory. So let's go back to just showing you the. So these are the 4 operations I was talking about. So you can see that the word line is always on whenever you do an operation. That's fine because you're always using the main racetrack. But you can see in the write operation, so just if you just follow underneath that word write written there, you have the incoming signal. It's in the orange, and you can see in the bottom panel that the skyrmion moves from its position 0 to about 0.2 micron on the micrometer on the racetrack. Recovery, of course, does not move because we do not touch the recovery. And you can see that you turn off the signal and this still continues to, stay at its position as expected. Now, when you have the read enable signal happens, your skyrmion starts to move, and you can see the V out. It only, like when it reaches the end, very end of the racetrack, the V out jumps into the signal. So you would have started your time reckoning from when your read enabled was started. So you can see from that to where your MTJ first triggers is basically that read out that you had, that L minus W that I mentioned. And you can see the skyrmion is essentially moving there. And now you can also see that we are moving the recovery skyrmion along with it, synchronized. And these control circuitry, of course, transistors are fast enough that they can turn it off. Magnetic phenomena, if you remember, if you don't know, works at, say, nanoseconds or hundreds of picoseconds, but transistors can act very fast. They can act in tens of picoseconds, so you can actually do the synchronization well. And this is all done in SPICE end-to-end simulation. So this is actually SPICE simulation that you're seeing. So now in the recovery phase, we all turn on the signals. The recovery signal is turned on, and you can see that both the skyrmions in concert kind of go back to where it was. So you can see that there is a little bit of a difference. If you kind of zoom in on this one, there will be a little bit of a difference because that depends upon how well the skyrmion registers under the MTJ. So like if MTJ is huge and your skyrmion is small, as soon as it hits the MTJ edge, it might stop because MTJ will trigger. So you may not exactly reach the center of the MTJ, but if you do the scaling and of the MTJ sizes properly, you can pretty much recover the same exact amount of distance that you went back. So you can see that as again there was this blip that happened because it hit that MTJ back again, and this one was actually from the recovery one. And now in the erase phase, all you do is that you just send the main racetrack skyrmion back. So I just want to show you the simulation platform that we used. So this is the modeling and simulation approach. So we performed some micromagnetic simulations using MuMax, and this is I'm showing an example of either a domain wall on the left or the skyrmion on the right. So you can see that this is just the read operation essentially. So in the read operation, again, the skyrmion in the domain wall on the right side, say it's down, and the left side is up. So in the middle is basically where you have the domain wall. So the domain wall is moving from left to right, and you can have the recovery racetrack also move in the concert. And the right, I'm showing you the same simulation done with skyrmions. So with these simulations and some work on what is called as the Thiele equation, you can actually extract a benchmarked analytical skyrmion mobility model, which means that if you put, say, 1 amp of current, what is the velocity of the skyrmions? You can actually work out depending on the material properties. So you can calculate an effective mobility. So we use that mobility to build this circuit model. Essentially what we have is this I is the drive current that you're applying, and this mu comes from this model. And once you have that, all you do is you have an integrator keeps outputting the the length at which the skyrmion has moved, the instantaneous skyrmion length as the voltage, and with the voltage comparator of where your MTJ is located, that's L0 location, you can determine if your skyrmion has reached or not, and that output is essentially the skyrmion, the MTJ angle, the angle that MTJ reads. If it's 0, then it's one thing. If it's pi, you can fix it in that way. It reaches pi, which means it has turned, it has arrived, and that can trigger an MTJ's resistance change. Now this MTJ model can be put into spice circuit of all the transistors, all the control circuitry. So this small model, again benchmarked from micromagnetics, can very well capture the skyrmion motion, and in principle can be extended to domain walls and bubbles and all of that. So let's look at the final, basically the set of results of energetics and optimization. So what I'm showing you in the left panel are the 4 operations, assuming about 50% or so of duty cycle for a very typical racetrack size. I think we consider about 600 nanometers. You can see that if you look at the labels, so this T1, T4, if you go back to the poster, you'll see that those are essentially the transistors. The track and the TRK, M, TRK are those are the recovery tracks, like what is the joule heating that happened or joule dissipation that happened in the tracks. So you can see that those are very small. Those are 10 to 20 femtojoule. The main energy consumption that happens is in the drive transistors, because you have to drive so much of current into the recovery, into the racetracks. So that can be, and the total, however, even with that total, I think we found that they can be less than 1 picojoule for this kind of an operation. Now this current requirement you can reduce if you go to some optimized material choice. For example, I'm showing you an example of the drive current that you can go down to if you can tolerate different kind of these damping parameters. For high damping, you can see that you actually have to drive fast because it's like a resistive material. But for low damping, you can drive with much significantly, like much reduced, like almost 10 times reduction of current. And you can, if you remember, the energy goes as I square, so it will be like 100-time reduction. So of course we have not done all the simulations yet. This is a work in progress, but you can also do some geometry scaling. Maybe you choose to don't have as long of racetracks. That will of course determine the type of memory, the memory sequence, the length that you can capture. But if you can make those choices, like clock cycle, for example, what is the maximum wave duration you can do? You can do some optimization of the scale. But anyway, anyhow, this racetrack is quite energy efficient because it's small. It's just a few hundreds of nanometer in length. And if you consider that, how will you even store this kind of? It's a linear information, first of all, because the time that you are recording is a direct linear information. So your readout and read in is simple. You just have a triggering circuit that does it. But so you don't have any complication in terms of recovery and reading. So that's why it's much more simple. Now, if you had to do this using a CMOS, you would probably use something like a count up timer or a Johnson counter, basically, which means that whenever a clock cycle arrives, you count one tick, and so that's how Johnson counter works. Now, if you look at the circuit of a Johnson counter, it's built of a shift register. It's a humongous circuit. So this has just 8 transistors and 2 racetracks. That's enough, and it can, you can do this. It's non-volatile. So if you consider all of those propositions, I think it's a very attractive option. So with this, I will end my talk, and thank you for coming to this poster session. And you can always reach out to me during the poster session itself using the Zoom meeting. I have attached the ID in the NanoHub discussion thread. You can also contact me off session or after the conference through the email. And also I acknowledge the following agencies, and thank you, and you have a good day.